Oh, go ahead. My name is Heidi FRITZ Martinez. I own a company called Remotor America, where I help promote American businesses and also provide global access to energy technologies. I worked in collaboration to facilitate about $30 million in energy efficiency funds for VFD applications, and I'm happy to help anyone in any way that they need. So feel free to reach out anytime.
Hi, I'm Pooja Tiple. Am I audible?
Hello.
Yeah. I'm located in Kitchener, near Toronto, Canada, and I'm recent graduate from Concordia University, masters, and majored in control system and power system. So when I saw a VFD as a topic, I wanted to know more about it and explore the field. That's why I registered for it.
Oh, very nice. Nice to meet you.
Nice, yeah.
Hello, I'm Michael McClellan. I work with a company called Tech4, as well as I manage an independent manufacturer's rep firm down here in the Southeast United States. So I'm in Atlanta, Georgia, or actually a suburb called Marietta. Was associated with Danfoss for a number of years, so I'm sort of familiar with VFDs, and just looking to get a refresher here. And thank you so much for inviting me.
Oh, welcome. Nice to meet you.
You too.
Well, we'll go ahead and go on forward, and please ask questions as we go through this. I also run a group called the Nikola Tesla's Today's Solutions and Collaborations, and from the beginning, Nikola Tesla was actually the inventor of the designed and patented the induction motor. That back that time was more of a two-phase. Now they went to three-phase, obviously. But he then gave the patent off to Westinghouse. He was the one that first put the generators and stuff up in Niagara Falls. I actually have a copy of his book back from 1904. I feel very gracious to have it. Got a lot of information in it. He's a very, very, very smart individual that was way ahead of his time. There's been many things that he had created and done, and so we have this group. There's about 2,500 in the group right now, and you're always welcome to join it. People share a lot of their ideas, concepts, energy generation types. It's been an interesting group. It's taken about 4 or 5 years to build the group. But they're very, very kind, helpful people. And we feel that if everybody gets along, collaborates together, we're just we're a better world from it. There's more than enough electric motors that need to be, properly retrofitted, especially in America compared to, Europe and Asia and different places where they've gone a lot further and deeper into applications. We always try to bring up, that because this technology is, high voltage, that, people use, extreme care when they open cabinets, arc flash. It's a lot of times they'll have capacitors built inside. So when you take the covers off, they have a residual voltage for a little while. Normally it's a 5-minute thing. So you normally want to wait at least 5 minutes once you take the covers off. Or if you do take the covers off, that power is totally down so that the discharge capacitors, have time to get, dropped out before somebody starts putting their hands in there. A little bit about us. I'm actually second generation, Heidi's third generation, and we have actually some grandkids that are starting to, get involved. Also, my dad started in 1953. He and 6 of his brothers all started motor remanufacturing companies in the Midwest after they got out of the wars and stuff, and they put together. There's still 7 companies still in the Midwestern area that are still under the FRITZ family, and we're proud of our heritage. We're glad that he, took the time, effort. And then a little bit by myself, I spent about 37 years working around the utility companies, all the way from the West Coast to the East Coast. I spent about 25 years in the Boston area, working a lot with National Grid, Eversource. I'm doing a lot of pilot installations when VFDs were first started being developed and applied to, application. And so a lot of my experience has actually been hands-on. Finding out what does happen when you put, large number of drives in, that you've got to be aware about noise and harmonics and, information that a lot of people, don't necessarily want to talk about. I've also been involved with the Electrical Power Research Institute on variable speed drives. So in 1995, there was a huge report written about VFD applications for plastic processing machines, and we had literally installed thousands of those around the country, and some of them even went international, because we were basically working on a fixed volume machine, and we were making variable volume hydraulics through running motor speed control on fixed volume pumps, and it had a great impact back then. They definitely oversized the pumps a lot more than they do today. And then even now, the newer machines are all coming out with VFD technology, running on if they're a hydraulic machine, or they're using VFD technology, running all the servo motors that run the mechanical balls and screws on machines, instead of using hydraulic pumps. Interesting experience. It did create a massive amount of savings, and we still do some of these machines today. I'm going to play this little video about.
When you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the superior adaptability.
So literally what we're talking about is that a induction motor has, like it shows on the left item here, that it shows these sets of coils. And actually I've been rewinding motors since I was 10. Because my dad didn't really want me to be involved in too much besides electricity, and so he made me wind coils for his winders and installers of rebuilding machines. And so I got a lot of lessons about this, and actually it's a real art and kind of a unique thing that is still done yet today. It's obviously in bigger machines than it is the smaller ones. A lot of them have turned away to being throwaway motors, because of the cost of automated machines to be in building them. But what happens is that you've got, this shows just one phase. So you've got one this is a 4-pole machine, they call it. So if you put 60 cycle power here coming off of the voltage, it literally shifts as it goes from positive to negative to where it powers which coil. And so first this one will get, part of the wave and drive, and then when it shifts, it'll shift to this one, the next one, next one, next one, and then it rotates. And then you have a aluminum, most of them today are aluminum barred or copper barred rotor inside that those magnets push against each other, and it starts rotating the field. This shows just a single phase waveform. A lot of them, obviously they are 3-phase. So they just have, 2 more sets of coils in here in between each, all the way around the rotating field. And it ends up making it a 3-phase motor. The reason why it's very impactful today to understand, which I think a lot of people are missing the boat on, how much business opportunity and how much energy savings can be done. That literally 70% of the world's power does go into electric motors. And still yet today, we've maybe hit 15% implementation factor. As compared to Europe, they're up in the 50s and 60% factors of utilization. There's been many studies of, how much impactful power could be reduced if it's implemented properly. And there's many incentive programs, around the world. So the breakup is that about 51% of it actually goes into motion. So it ends up being conveyors, things carrying materials, mechanicals, like in steel mills and those things that some of it can be adjustable speed put on it, some cannot. But there are technologies, we'll get into a little bit further, that which are called, they call them soft starters today, but there's also, they have some that are out there, power factor controllers. The other area, about 19% of it is into, HVAC, fans, pumps. About 16% is lighting, and then the other is electronics. But where it seems to be that I think a lot of the lobbyists have got in or done or whatever, they're pushing a lot into this area, into lighting. And so it, makes an impact of maybe, if we cut 16%, that takes about an 8%, the total global power, that they could ever accomplish helping the world with lighting. Electronics, there's not a whole lot you can do with that because, you've got, SCRs and switching and stuff that, need to operate, that you really can't do much with that powered load. A lot of it has been implemented over time. A big part of it, a big focus was on buildings, putting on fans and pumps, but they tend to walk away from the motion side because the motors are in the critical process. And so they tend, it's hard to get engineering to accept this. So they tend to say, oh, well, it's a constant torque load, you can't do much. That's really not the case. We've proven that over and over again. So the original electric motor was simply, you had L1, L2, and L3, which are here where your lines are. These show the contactors. These were the thermal overloads, and then it hooked to the 3-phase motor. And what literally happened is, just with the start-stop circuit, it turned the coil on and off, and it closed these contacts. So what literally had to happen is, as soon as you did that, you're putting 230 or 480 volt, depending on how you have the motor connected. You're putting that power directly to the motor. Well, the motor is setting here at standstill, so you get what they call inrush current. And normally the inrush current will be 5 to 6 times the running current after it gets up, because once it gets going, it actually creates a counter EMF voltage inside the motor and resists the current flow. So that's why it starts up really high, runs down. So there were many, things back then, where they said, okay, well, in order to reduce that inrush current so they didn't have the bigger fuses and the power transformers and the generators had to be big, they did what they call part wind start. So they would take literally half of the winding, start it, and then kick the other half in after it was running. So part winding starters, you still run into them, and especially in the irrigation industry, there's a lot of those still out there. Then they, got a little trickier, and they created what they call wide delta starters. So you had your L1, L2, and L3, which is where it finally ended up connection. But in the first part, they literally connected the motor, and they shorted this out in basically the 6, let's see, it would be the 12, 11, and the 10. They hooked this in what they call the Y configuration. What that literally did is, instead of putting the 480 volt across here, by connecting it in that circuit, it would only put 277 volts across that. So the motor would have more torque. It would still reduce the starting current. And so there were a lot of these in European machines. They had a mandate that this goes back 40 years ago, where they had to have a Y delta starter on any machine over 7.5 horsepower. And so that's moved to that. Then what came along is the soft starter. And there were 2 patents that were developed by a guy named Nolan out of NASA down in the Houston area. And he was doing it basically so that when they put things into space, they had a limited amount of power. So they definitely wanted to conserve it. So he took SCRs and would slowly switch them on, and it created soft starting to motors. These are the 2 patents. One was the device where he patented the variable frequency drive, and the other was where he patented the soft starter. And that was back in 1975 where he came out with the. So there's a couple different types of soft starters out of it. This is the type where it's just it soft starts it, and then it has a shunt inside that brings it all across the line again after it's running. The benefit is that you can regulate through the screens. You can regulate how much voltage and limit the current as you're bringing it up. So it's a wide variety of applications. Then they've came out with a little bit more advanced type that actually have what they call soft start and soft run. So when the motor is not fully loaded, you really don't need to be giving it a full 100% voltage. So this device actually stays connected, keeps the SCRs in. It automatically watches the current, voltage, and torque of the motor, and it literally regulates that power. So this is more of a circuit that is out there. So you've got, SCRs here, driving the power to it, but and then after it gets up and running, then they have these bypass contactors. A lot of them today have built this contactor now inside the units. Some still have an external run contactor on them, when it's up to speed. So literally once it's up to speed, it doesn't really save any power on most cases, unless you go to the soft start, soft run type control. So what it's literally doing is, as here is the voltage waveforms that are coming from the power line, And what it does is it literally slowly switches it on. So it doesn't actually allow the SCR to pass until it gets to this point, and it's a very small amount of voltage. Then as it ramps up, you can see it just constantly, we can regulate how fast it's bringing that waveform to the motor. And so it ends up, creating soft start. This is the device that I've done a lot of experience in, and have learned a lot over time. Installed low voltage machines, down to a quarter horsepower, up to 5,000 horsepower medium voltage stuff. And they all have, various opportunities. But what we have to realize is we're building a non-sinusoidal waveforms. And so this is what they call a bridge diode. And really what it does is it takes the three-phase power, which is your original sine wave coming off the generators, and they put what they call a link choke in here, and that's just to slow down current flow to the capacitors and current flow to the transistors, so that it doesn't surge, because surging, ends up causing a lot of factors, especially on the old GTR, which were gated transistors. Now they went to IGBTs, which are isolated gate type transistors. And they've also got the switching up a lot higher. So what happens is we take this AC power, it inverts it here and gives us these ripple voltages here. And so then they put filter capacitors in there across here of the bus circuit and literally smooth that out, because you want basically very clean DC before you give it to the transistors to rebuild the output. And then what it does is, this is a 6-pulse transistor type output. And so what it does is it literally builds pulses in here to rebuild the sine waves. The back form is the current waveform, but literally the input, and I'm going to go back to one of the original screens here. This is what you actually see. So you see that from that bridge circuit, you see the pulsing going in here. So this is the current waveform. That's the voltage waveform. And when you put it into a circuit, they all have a difference in every circuit, because it all depends on what is the transformer size, what's what they call impedance, or like resistance of the transformers, and what is the power source strength and power capability to determine the power quality. So the input, this is the voltage you'll see, is that as this PWM, especially if they're lighter loaded VFDs, you'll get more ripple. And the code is to keep this below about a 2% voltage distortion. But you can see the output, this is actually a scope reading of the voltage output. And so you can see this has a multitude of pulses that are regulated, and they actually take up to now about 12,000 pulses per wave. So with electronics, they've evolved a long ways, and they can do it, do switching very fast. But again, that can if you're not aware of what we're putting into the circuit, when we first put machines on in the 90s for Milton Bradley Toys in Massachusetts, we installed about 70 of them. We learned a lot real quick, because that hadn't been done before. And so with all of this pulsing, we had to come back and do what they call a harmonic study, and we had to determine how all those circuits came out. And it was like probably back to college days of the resonant circuits that you create. So it's all controllable, but it's important to be aware that, when you do install something of any number of controls is when it comes in. I think in some ways it's gone a little bit too far. Then they, now want to force people to what they call 12 pulse, inputs, reactive front ends. It's overdone a little bit. That all drives up the cost of the product. And it's just better to look at it, as you're going along and what you're implementing. So again, this was just a detail of the diode bridge input, went to the DC bus circuit. And then there's a book that I kind of call my Bible. It's actually for members of ESA. My father used to be a chapter president and actually a director of that organization. It's 2,500 companies in the United States. Worldwide, it's about 3,000 to 4,000 companies that all share information, data, and they have this pocket engineering handbook that really gives you a lot of details of what the winding diagrams are, how the actual current should be, on the motors. So you can do, a little bit more information about, what you're dealing. It also has a lot in about how when you, are controlling a centrifugal pump, how you get the affinity law, what happens to horsepower and speed. So you do understand where the energy savings is coming from. So the issue about, I'm going to jump into a pumping application, is that it's important as we're regulating, that speed, that every pump has what they call a sweet spot of where it actually will pump water and won't pump water at certain speed loads, and where its ideal efficiencies are. There's a friend of mine actually down in Australia that actually gives a very good class on, and he's got a software tool that's kind of unique. I'll go into a little bit later, that actually, gives some tools so that you can pre-qualify the application, much earlier. Also, there are some losses that are inside the VFDs when you install it. So you've got effects of the transistors, the diodes, and it ends up being on average about 2 or 3% in power loss, developing the power. Again, this shows the PWM, as it's fired back out. Again, we went over this already, and so literally what we're doing is that if we slow the hertz down, normally it's 60 cycle, so you'll get 60 pulses of sine wave. So the motor on a 4-pole machine, if you do the math, it ends up being on 60 cycle. The motor will run at 480 volts provided from the inverter, and it will at 60 cycle will give full power and torque. When we slow it down to like 30 hertz, the motor will literally run half speed, and depending on where we're at on the pump curve, and also the cube factor of horsepower, you'll end up saving in terms of power. So at 30% on a pump, or 30 hertz on a pump, you'll actually be running half speed, so you get about half the flow, but it's a cube factor, so it's 0.5 times 0.5 to 1.5. So the actual horsepower is only 1/4 of the amount running half the flow. So that's why it's important to engineering always designs, motors to be oversized, because they don't want to run into a situation. And the pump oversized, as it has a wear factor, they want to always be able. So a rule of thumb used to be about 125%. So most motors are running faster than they need to still accomplish their flow requirements, and then they do it with valves and those things to cut it back. So the key is to get that understanding, and I don't want to get people hung up on that this is really that complicated. Literally all we're doing is we're building a variable power supply that we can speed up and slow down the motor. There's a lot of controllers out there that are have 200 parameters in them, and you have to utilize their startup people. And I don't believe in that. I think you go to Asia, you go to Europe, everybody is very well, implementing these on, most electric motors because of the amount of power that they're using and how we can control it. So we're literally just controlling the speed, the frequency, and then the output power as we're going through. This happened to be, another, circuit that they, a little bit more detailed to what they're doing. This has the diode front end. They added the resistors in here to slow down the current. And then they have a contactor after it gets up, gets the capacitor charged, and it shorts that out. So this is a shorting circuit. They have, some Hall CTs in here, to monitor the currents. And then they have some, diodes starting here into the feeding the capacitors, but then they have, again, capacitors here. So they have a capacitor that starts, it's all just to get this DC power supply up to par before we start turning the transistors on with output. And this is a little bit about the pocket engineering book I want to talk about. Something I see a lot happening in industry right now is there's a lot more motor failure than there was a few years ago because a motor doesn't like imbalanced voltage. And what tends to happen is, especially out in California, is we're adding a lot of solar. And so the voltage effects of compared to where the motor was actually designed for are getting off performance. And so here is in this book, it actually tells you the effect that, if you're, off by, 5% in voltage imbalance, you're supposed to be derating the machine, to about 75% of its value. And then if one phase is imbalanced of the other, you're also supposed to derate. So that's why more motors are happening, because they're allowing residential circuits to put a lot of single phase solar in, and so it's upping one set of the phases on a 3-phase circuit. So when it gets out to industry, so there's a lot of issues about power quality. And on June, I think it's June 15th, Heidi, I think we're having a webinar about how to clean up, cost effectively the
20th.
What day is it?
The 20th?
Okay, June 20th. Yeah.
Okay.
And we'll post it on our sites, and we'll post it on the Nikola Tesla collaboration group. But we go into in-depth about ways to cost effectively, keep power quality high. This is part of the reason why we have even seen when you put a VFD on, because we're isolating the input to the output, we're able to still control that voltage balance. So we've literally seen where you can run, really imbalanced voltages and, out on the primary, but the motor with a cost of, a good VFD, you can actually regulate each of those phases into balance, so you don't have to upsize, and the motor will run a lot cooler. We also utilize the technology to make single phase instead of using a single phase motor, you only have single phase power. I mean, you got 2 power lines there, but we can convert it to DC, and with proper sizing of a 3-phase inverter. Then we also have single phase input inverters. We can build through 3-phase. The 3-phase motors are much more efficient than a single phase. On average, a single phase motor is about 70% efficiency, maybe 72%, and a 3-phase is up in the 90s. And so just changing a single phase circuit out with an inverter, you do have a 3% loss in the inverter, but your total control, it saves a lot of power. We've done a lot of remote applications where They only have single phase power, especially in the Midwest. And we're running 3-phase motors, up to 50, 75 horsepower, single phase input. And we're able to help the power company because it doesn't surge it. It brings it on softly. So, that helps. Was there a question, Heidi, in the chat? Do you read what that chat is? Or was that just somebody know?
Not that I see.
Okay. Again, then this is a more, again, complex circuit that they show. And all we're really showing here is we've got the base circuit here, but this is the control input, so that we can actually, these are diagrams showing the original VFDs were not digital at all. So you had to set up all of those curves and stuff. This shows the little diode or little potentiometers that you had for each one of the circuits, because we had no way of digitally, saying we're wanting this value, we want to tell this amount, how much to fire, how the pulse was. So you literally had to tune all those circuits. So the physical size of the VFDs, when I first started, I think a lot of them were like a phone booth. Today they're like, less than an eighth that size. And a lot of the smaller inverters, are down clear to the size of about the magnetic starter, especially in the, lower horsepower is up to about, 15 horsepower.
You do have a question now.
Yeah, what is it, Heidi?
So Michael McClellan asked, why use Hall effect sensor and not a current transformer?
Maybe he could join in that and explain his question a little bit more. Do you mind?
Yeah, I was just trying to remember why they don't use a full-on CT. I understand that Hall effect sensor is something quite different from a current transformer, and I can't remember why they went to the Hall effect transformer. Oh, you know what? It's coming back to me. I think it is because the Hall effect sensor does a better job at frequencies other than 60 hertz, which a current transformer does not do a great job of. So maybe I answered my own question. I'm sorry.
Yeah. No, that's fine. I'm glad you
You're the
asked the question.
expert today,
I'm
Michael.
glad you asked the question because I do understand that's why they did that. A CT doesn't have as much inductance at low frequencies, and so it's hard to pick up and they need speed, especially to protect the transistors and the diodes. So a Hall effect sensor will read that again much quicker. They had more failures, I think, when they used to just do it with CTs, especially with the old GTRs. But everything was a much slower. When they first had the GTRs, they would only put 6 pulses out. So the noise level of the motor, getting all those square wave forms into the motor, it had to absorb a lot of that, create a lot of heat in the winding, also. So I appreciate the question. So I kind of went through that. So literally, most of the VFDs today, do have the digital keypad on the front end. And this is the main power circuit. So you got your 3-phase, here. This is actually the DC positive, so that I'll go into a little bit why they do that in a minute, but and then you've got your UV and W, your output, which is your 3-phase to the motor. So it's really your input, then you have the power to the control. They also have this this is what they call the DC choke here. That is what we were showing earlier in the circuit. That's the inductor that they're showing here. So again, a lot of the later versions of the drawings, I don't know, maybe are sometimes meant to intimidate. I'm not sure what, but I like to keep it simple. And then they show the power supply with a circuit breaker. We highly recommend that when you put it in, that you definitely use a fast acting circuit breaker to protect diodes and transistors, or put in fast reacting fuses. I've seen a lot of real high spikes and stuff, and it ends up going in and damaging the inverter. And these are not an inexpensive device, so it's much easier to change a fuse. So you need that response here. So we put in fast acting fuses in the panels and stuff that we build. We use a lot of the 434 fluke meter to do some determinations, on bigger applications before we get involved, so that we could come in and sense what that power quality is. So it literally, reads the waves that shows the 60 cycle power, reads the voltage line to line, and line to neutral. So we get the full spectrum. It shows us our imbalances. It shows our noise, any existing harmonics that could be coming from the power line. We'd like to take a view of where we are to begin with. I'm going to run this. This is a little bit about why I don't sell fluke meters, but we really swear by them. So.
Introducing the Fluke 438 Power Quality and Motor Analyzer. The Fluke 438 is a multi-purpose test tool designed to improve troubleshooting on electric motors and minimize downtime. Whether you're in a process plant or discrete manufacturing, electric motors are critical to your operation's success. The Fluke 438 lets you quickly gauge electrical performance, power quality, and mechanical performance of industrial motors. Using three-phase electrical measurements on the input and motor rating plate data, the 438 calculates torque, the most critical mechanical performance variable, speed, load on the motor shaft, and overall efficiency, without the need to install mechanical sensors. All this with a single tool, and all while the motor is running so you don't sacrifice uptime. Power quality issues, such as unbalance and harmonics, can cause motors to run hot, eventually stressing windings and accelerating failures. Motor failures lead to costly downtime, and the cost of waste associated with inefficient motors adds up. When testing direct online motors with the new Fluke 438, you get both power quality information and mechanical performance data in the same test with a single tool. With an intuitive user interface, optimized current probes, and at-a-glance motor status screens, the Fluke 438 gives you the motor troubleshooting information you need to make better maintenance decisions and keep your plant up and running. Contact your local Fluke representative to learn more.
So the reason why I like to bring that up is that he's exactly right, is if your imbalances in voltages, if you already have noise issues in the plant, and they're just not picked up by using your normal volt and amp meters. They're not quick enough responding, they can't see it. And this shows what they call the harmonic order, which is basically the frequencies that there is distortion happening. And when you put in a 6-pulse machine, you get a lot of what they call 5th, 7th, 11th, and 13th harmonics, which today we're working actually on a project for a company up in Ohio where they have they installed in a data center about 40 VFDs. They also have the data center, loads in there. They have the chillers that now, because the building is not loaded as heavy as it was in the past because of COVID, the chillers are not running at full load. Some of them had VFDs on, some don't. And literally it's thrown the power factor off into like 69%. And so any below 70% power factor, the power company's hitting them with a $25,000 a month penalty. A lot of people, went away, oh, well, I put a VFD in, it's got, proper, inputs and stuff, and it's got a line reactor on it, but it's not, but again, it's all an LC circuit, both inductive and current loads are going on out there. And that's why I like, the Fluke meter, because it allows us to actually see what's really going on. So again, this is the what they call the fundamental, which is what the voltage is here. The resultant is what the power company bills you here for load power. So you can see as we get these various harmonics, and a lot of this happens in heavily inverted, lighting gives off, DC machines give a lot of different amplitude, various harmonics out there. And so what happens is, by this being off, the resultant power is quite a bit higher. This happens to be one type of an LC. They put inductors and capacitors, in parallel and series into the circuit to clean up in the, this happened to be in the wastewater industry. This is okay if it's actually a more of a constant, load capability. But again, the Fluke meter is telling us what that PWM is looking at. It's each individual motor, and it's showing the resultant voltages, and it gives us those values. This is before and after the harmonic resultant that was in there. So you can see that these PWMs and stuff were distorting the voltage here to about 451 volts in resultant true RMS power, and about 138 amps. So basically the power is amps times volts times power factor gives you your kilowatts. So you can obviously see that this resultant voltage was distorting the power readings. And nowadays the power company has smart meters on. So the before and after of actually putting the proper filtering in place, which cleaned it up, went to 443 amps at 128 amps. Calculation. I guess I don't have it on this particular slide, but the resultant was, just by cleaning up, this is just the harmonic content, into the building, it ended up saving right at about 15% of the front end power just from harmonics. Then when we cleaned the power factor up, we end up bringing in and eliminate all those power factor penalties in addition. So we like to see a building cleared up. We have a filtering network. Besides, this is what they call a static filter. We also have a active front end one. And actually I learned about that when I was flying on an airplane going from Boston to Washington, DC. And there was a guy there from the military defense contractor. And he said, hey, we got to talk about what we were doing. And he goes, gosh, he said, well, why don't they put active front ends on, on these and clean that up? So we actually work with a company that actually has a lot of patents on that technology, but they actually do firebacks to compensate for this, and it's automatically resonating. And again, on the 20th, Heidi said we're gonna give a more in-depth detail of how those active front end filtering networks work. It's kind of a wave of future that's happening because power quality is so important. And, even the interruptible power supplies, a lot of people don't realize they're actually just a VFD with a fixed input and output, frequency. And so they'll put off some noise factor, and we've run that in some building. You also can go online to easa.com, and you can find this trifold brochure, so that you can literally determine what is happening with the motor. And this gives some examples of when you have the spike voltages and stuff, how it shorts or turns the coils out. This happened to be one where the imbalance in power, you can see, the voltage was so low on this one phase that it all was picked up by the other two phases, and it literally just smoked the coils out. And it called a lot of times they call it a single phasing, but a lot of times it's actually just really bad imbalance power. And the book's very good. I mean, the little pamphlet, this shows where it, shorted in the slot. A lot of time that's from, mechanical rub where something, the stator in the rotor of the bearings may went out, started dragging, so it burnt the insulation, because the windings need to stay isolated from the steel. This shows a phase-to-phase spike, that happened. So being motor people, we like to look at, what's really happening in the motors, not just, not just slap something on and say it's all going to work. This is a little bit more about the digital operators, that are on the front. I also give classes of specific, drive control applications. We've done it for, extrusion machines, because you have, encoder feedbacks, and, those most drives you can use in multiple modes, whether it be, centralist vector, full vector, where you're, have the encode feedback, or you can have it in volts per hertz, or you can have it regulated volts per hertz, which is more the later ones for fans and pumps. So it, adjusts the curves and then automatically regulates. Most of the, the other thing you need to be aware of is when you install the controllers, that you are aware of, if it's inside of an enclosed environment, that you have air room around it, and also do a thermal capacity of in that room. A lot of the controls today are what they call 50° C rated, so they're a little more lenient to higher temperatures, but it's still, still a factor, especially if your supplier is supplying what they call variable torque drives. What that really means is they're taking a constant torque drive and derating it to only 120% capability, because they know that typically a pump doesn't work that way. I tend not to try to do that. I try to use constant torque drives, use them in the variable torque mode. That always gives me 150% factor on the transistors, which mean that the actual transistors are rated at 300% capability. So even if the guy surges them or shorts them, you won't have transistor failure. They have, a lot of data screens you can, set up. You can scroll into them, all the various, inputs, outputs. This is the control circuit, that shows, they put a DC power supply, in here. So it has like 24 volt, power output. Then it can go, you can select through the keypads all the digital inputs of what they're doing, which analog signal you're drawing, back from, if you're putting it in a pump application for PID loop, or, those things. And so, again, what I like to do is, for specific industries, is, give some classes on actual application. And then I like to use the ones that have the very simple manuals in it that are more dedicated, that you only have 2 or 3 parameters to set up. So you can get that pump up and running quickly. Also, there's, various softwares that are out there that you can download into various drives. So they're already preset up for pumping applications, lead lag, multiple pump, sequencing, and all that's, set up. So again, that'll be in one of our more of the pumping classes. And we go into detail about torque curves and those things at that point. Again, these are some of the various parameters inside, deceleration, acceleration modes, how fast it's speeding up, you can set the upper and lower frequency values, the high limit and the low limit. So if you know that the pump won't pump water at anything lower than 20 hertz, you want to set the VFD so it doesn't run any lower than 20 hertz. So it just doesn't sit there and cavitate. And then you want the upper limit. A lot of times pumps were designed again for overload capacity. So we highly recommend that you look at the output currents, and you can actually save the motor a lot by not having it run into service factor, as high. So we set the upper limits based off of what, output current is, and true flow requirements, with the dimensions. Again, looking at those various, input voltages. We also, from taking a few pre-readings, we'll give a recommendation of which VFD we should actually even supply, because there are 480 volt inverters, but those are rated roughly plus or minus 15%. So you can see voltages up as high as 510, 520, but there's application in some of these older mills and stuff, especially up in New England or down in the Carolinas, where a lot of the motors are even still running on 575 volt, where you go up to Canada. So you want to get the right input voltages set up on the drive controls, and we tend to want to ask a lot of questions when people are looking into it. Again, the cause factors that are out there, under voltage, out imbalance, cabling issues to the motor. What they're talking about for cabling is that when you put this PWM going out.
Just a marker for time is you're about 2 minutes to 11.
Okay.
Okay.
Yeah, anyway, that's fine. So when you have this PWM out, going out, depending on how long the lead lengths are out to the motor, you create a different amount of inductance going out and resistance to the motor. So literally, you're a voltage supply. You'll see these extra spikes, and that's what destroys, especially older motors that had, lower. Seemed like from about the 85, 90 on, they all put in spike resistant wire, but some of the earlier ones didn't have it. So you had, motor failures. So, back to the proper metering, we definitely recommend the true RMS meetings, so you can actually look what your power company is going to see, through their metering. There's also these hobo meters you can stick in for just preliminary load factors, and then, straight volt and amp meter. Again, so that's pretty much the end of what I was going to talk about, on this, point.